Okay, great. Hi, the topic talk about incorporating word order in Glove word embedding. Um, word vectors play a main role in extracting good information from unstructured text, and they have been used in many tasks. For example, finding word synonyms, word analogies, and syntactic parsing. Many vector representation model has been presented for a long time, such as word2vec, global vectors for word representation, and the most recent ones, the BERT, GB2, and CTRL. Many of these models work on the base of a word defined from its surrounding context. However, some of these algorithm doesn't take into account the word order or the position of the word around in the context. This research focus on GLOVE, which is the global vector for word representation algorithm, to consider the word order in the context. So what's GLOVE or global vectors for word representation? It's an unsupervised algorithm. It's been proposed by a team in Stanford University. It works on the base of a word can be defined from its surrounding. It builds vectors using global bilinear word, global bilinear regression model that discard all the zeros and reduce dimensionality and find the best word vectors. So the problem that our research tackles is that this algorithm, GLOVE model, fails to consider word position explicitly. And the goal is to improve GLOVE to add explicit representation of word position within the context window. And for that, we will use the word as a word embedding algorithm, and we will use a group of ground truth datasets to evaluate the presented system. There have been a lot of work already published that been taking into account the explicit information, such as the one in 2017 that uses the anagram technique to create vectors from the word characters, and also the one in 2019 that used the kernel principle component analysis to add like explicit information. And another work that used the implicit update, that means it affects the algorithm itself or the steps there, such as the one 2019 and 2020 that boosted the weights of target word on the concurrence matrix to increase the chance of finding their similar words. Our research is different from these already published work, is that it improved the GLOVE algorithm by explicitly considering word position in the context. So for that, we proposed three methods. The first one called direct concatenation, where we have the words around and have their vectors, then we concatenate them. The other method, reduce concatenation, because we will have a big vector size, we will reduce the size. And the other one, we will reduce the weight of co-occurrence in the vector, trying to like lessen these high weights that coming out from the concatenating of two vectors or more. So the first method is direct concatenation, and we here show an example. For example, we have this text and we have this pivot word, for example, from the text, which is the store. So we will go I+1 and I+2 into this word. And we can see we have these vectors for the words around the word store. Then these two vectors will be concatenated to have this final direct concatenation, sorry. The other method is reduced concatenation. For this one, we will have also an example here, like we have the pivot word for the store. We will have the two vectors, but here we will have the half of these two vectors. So we will not have the whole vector, but half of them. So the final vector will be small, or the normal one that the GLOVE has. The third method is the same as the first one, except we are dealing with the weights where we are reducing the size. And we can see here that we have the two vectors for the context words. We have the final vector, but this time the final vector is not the same the original vectors, it has been the weight has been updated into some value. Let's say it's we call it alpha or weighting, some weighting values. Like here we are multiply by 0.5, like we're cutting into half. To evaluate our algorithm on the baseline, we collected a text that has a size of 8.7 gigabyte. We cleaned that text and tokenized and lowercase, and the end is like 100.3 billion tokens. And to evaluate, we had two tasks. We evaluated on the analogy task, and the other one is the similarity task. And for that, the baseline gonna be the unmodified glove without these methods that we presented, with vector size of 100 and window size between 2 to 10, and positioning between ±1 to ±5. Here we have the result from the analogy task. So we show here the baseline, the glove, and the other three methods, the direct concatenation, reduced one, and the weighted direct concatenation. And we show here the relative improvement from each one. We can see here that two algorithms, the direct concatenation and the weighted direct concatenation, they were able to get into good results comparing to the others, the baseline and the reduced one. But the highest one or the best one that led to better results is the direct concatenation, which shows on average 36 relative improvement over the baseline, while the weighted direct one shows 15. So the best one is the 36%, a 36 relative improvement. And for that, we will use this one because we already know which algorithm is the best. So we will compare with the baseline, the best algorithm for the next task, which is the similarity task. And in the similarity task, also the direct concatenation showed the best performance over the baseline, with 34% relative improvement over glove or the baseline. So for conclusion and future work, the main goal of this research was to incorporate word order into glove. And for that, we proposed three methods. And the algorithm that reported the best was the direct concatenation with best performance over the two tasks. It's greatly improved glove and led to better results. And for the future work, we suggest fine-tuning of the Wove to find sentence embedding and compare it with state-of-the-art sentence embedding algorithms. And please, if you have any question, let me know.